Hi, in this video I'm going to try to explain the underlying idea of bagging. I won't try to explain the details of any specific bagging algorithm, I'll just try to give you the underlying idea of all the bagging algorithms. You might remember that in previous videos I talked about these dartboards. Let's just imagine I have two dartboards and then this is the bullseye, and I might throw a lot of darts towards these dartboards. And I'll do it in different ways. For both of them, I'll throw them with a low bias, but for the first one, I'll throw with a low variance, and then the second one will have a high variance. So then, throwing these darts, it'll look something like the darts over here will all hit like close to the bullseye, but over here they will have a higher variance. So the goal of bagging is to go from this case to this case. I'll try to reduce variance, and this will be the goal of bagging. Great. So I'll try to motivate the core idea here. If you think of these points now as points in a coordinate system, then they'll all have x and y values. So now it would kind of make sense to do an average on all of these points. So if I averaged all these points out, you would probably imagine I would get something like maybe this point, which would be pretty close to the middle actually. What a surprise. So the idea we're going to use is that averaging reduces variance. So I'll try to formalize this by an example. I won't go into justifying this a lot. I'll just try to convey some intuition here. So let's say I have n random variables and they're independently and identically distributed. We could probably let's just think of them as let's just say they're normally distributed like this. Okay. So then clearly the variance of each of these guys is a sigma squared, right? But so now I want to think about, well, what about the average of these guys? The average of these random variables. This will in turn be a new random variable. The average of the random variables will be a new random variable. So it'll also make sense to talk about the variance of the average of the random variables. So if averaging reduces variance, then this should have a lower variance than each of the random variables. Should have a lower variance than sigma squared, right? So I'll just try to prove this to you and show this. It'll not be a proof, I'll just show this. And to do that, I'll just need two things from probability theory. So I'll just remind you that if I have the variance of some scalar alpha times a random variable, then this will be the random value, the scalar squared times the variance of the random variable. And also, if I have the variance of a sum of n independently and identically distributed random variables, this is very important. They have to be independently and identically distributed. Then the variance is linear, and then the variance will be the sum of variances. So I'll use these two facts, and maybe you might already see what is true, but let's try to just go through the derivation. So by the first thing, so let's just skip the numbers, this is 1, this is 2. So by the first rule I just reminded you about, I can have 1 over n outside, I just have to square it. And then I have the variance of the sum of xi's. But so these are independently and identically distributed, right? This is what we considered in the beginning. So each of these guys, well, I can move the variance inside the sum. This will be the variance of each xi. But I already know that the variance of each of these xi's is sigma squared, right? So I'll just write sigma squared here. But this will be the same as 1 over n squared. I just forgot the squared there. It'll just be n times sigma squared. So then this n will kill the one of the n's, right? And it'll be sigma over n. So this actually means that this new random variable, which is the average of the previous random variables, will actually have less variance than each of the random variables, and it'll actually be a factor n smaller. Great. So this is definitely true for random variables that are normally distributed. You could actually just try to look at this and you'll see that I didn't really use the fact that they were normally distributed. I just used the fact that they were independently and identically distributed when I used rule 2, which I applied here, right? So this is true for random variables that are independently and identically distributed. So this is all fine, but what we really care about is hypotheses, right? We have this target function f from x to y, and we want to approximate this guy by some h, and we have data to do this, right? So we might maybe think of the data as realizations of random variables. I mean, each data sample is independently and identically distributed, right? This is what we assume. But what we want to do is we really want the hypothesis, the variance of the hypothesis we learn to decrease, right? This is what we care about. So we'll apply the same idea here. But suppose for a minute we have a lot of data sets. This will not be the case in the real world, but let's just suppose that I have dataset 1, dataset 2, all the way up to dataset k for some large k, right? Then I could also learn hypothesis for each of these datasets. And I mean, if we are in a case where when y is like some real, like we're in a regression case, right? So let's just write this as a case. Y is the real, so we're in a, like a regression thing. Then we could also make a new function that kind of aggregates these and have it be the average of what each of the guys say, right? So it'll be something like this. Then it'll be GDI, right? So g of x would be the average of what each hypothesis say. And in this kind of sense, because they're learned on different data sets that are independently and identically distributed, then the hypotheses will actually, you can also think of these as random variables, and then the variance of these random variables will actually also decrease as you can actually do the exact same thing as we saw up here, right? So these are random variables, and then if we find this guy in a kind of then, well, the randomness over here will influence these guys, and we'll be able to kind of decrease the variance by doing this trick. So I'm hand waving a bit here. I don't want to go into all the messy details. Great. So unfortunately, this is not the case. We don't have all these. So what we'll do is we'll do something called bootstrap samples. Bootstrap samples. So the idea is you can think of our data set as maybe, let's try to draw it like, think of our data set as like a rectangle. Like, it'll be a lot of data points. I'll just draw it like a rectangle, and then each of these small rectangles will represent a data pair. So then what I'll do to kind of simulate this is I'll create these new data sets where I just randomly pick a point from the original data set. So maybe I'll pick this point, I'll pick this point, I'll pick this point and this point, and I'll just continue doing this, and sometimes I'll pick the same point. I'll have replacements in here, so I'll pick the same points a couple of times. So then I get a new data set. I'll do the same for the next guy, and I'll do this for all of them, right? So each time I put a cross, I'll take the corresponding data point. So then I'll get a lot of samples, and then I'll learn. So the algorithm now. So the idea of bootstrapping is now, well, take your data set D, then create D1 through DM using this technique I just showed you here. Let's call it maybe DK. And then on each of these data sets, learn G1 up to GK, and then output like a final hypothesis that's then like an aggregate of all the others. It could be like an average, as we saw before. So this is the rough idea, and I won't go into more details of it. I'll just mention if we had the case. So now I said this was a case where y is the reals. We could also have the binary classification case. In this case, you could have had g of x to be like a majority vote of g1 through. Let's just use the same notation, g1 up to of x up to g dk of x, right? So you could also do it in other cases with the binary classification. So this is the rough idea. Great. Thanks for watching.